shut the gates, forget us now. Tides are changing. Can you hear the sound? Can't stop us now. We're not back in town, know what we're doing. Things are about to change, it's evolution. Voices shake the ground, you feel it moving. We the revolution. We the revolution. We're the ground beneath your feet. We're the whisper in the tree. Do you feel us watching? Hunger in our eyes, victories on our minds. It's our time to rise.
All right, good evening and welcome everybody. You know what? I'm going to burn a couple of snoozes here. It's fine. So how's everybody doing tonight? My name's Obi-Wan Pez, and this is N Simplex Pachinko, in case you haven't been here before. We're doing all right on this side of the pond. Again, anybody who doesn't know, so we are an American family living in the UK, currently looking at... Okay. Hey, Heffer. I was wondering why it played my intro again. No. Different person. So yeah, we're living in the UK, currently looking for a new place to live because our landlords would like to live here again. I do suspect it does have something to do with the new law that's coming into effect in May, but hey, whatever. It's their place. They can do what they want with it. So, welcome on in, everybody. Matt and your twerking duck. Zach and Penn, I heard you come on in. And everybody else who has popped in. I hope you're all having a great evening. We're doing all right here, like I said. Yeah. Just generally speaking, doing all right. We are actually packing up to go on a nice little vacation to Norway. So we'll see how that goes. It's always very interesting. I don't know the language, so like French is one of those that I can get away with. German was iffy, but it still worked. France obviously worked great. Still don't know the language as well as I need to, but nonetheless. And even, dare I say, Greece and Denmark went fine, because everybody speaks English, and when they don't, you can Google Translate a bunch of stuff, and it more or less works. So, good times. Right. So tonight we're going to go a bit further through the Galilei and Huygens paper that we were looking at last time, Math Education, discussing art and science and how they sort of went hand in hand with the father-son relationships in both families. So we'll see how it goes. Currently, Dr. Papadopoulos came up with, again, the relationships that existed between the fathers and the sons. Both of the fathers, Konstantin Huygens and there we go, Vincenzo Galilei, were both interested in music, and Dr. Papadopoulos found it interesting that both of the sons then went into science, trying to figure out the world. So, without any further ado, unless anybody has anything they want to talk about, okay, so going over this a little bit again, Galileo Galilei and Christian Huygens were both raised in environments conducive to their intellectual development. As children, they both had the opportunity to meet musicians and other artists who passed by the family home. Vincenzo Galilei wanted his son to become a physician, while Konstantin Huygens thought his son would follow in his footsteps into a career in diplomacy. Neither son followed his father's path. Galileo became a professor of mathematics, then of mechanics and astronomy, while Christian lived mainly on his father's annuities, then on those of Louis XIV, who took him under his protection, and later on from some of his inventions' income, principally watches and clocks, for which he had obtained exclusive exploitation privileges from the King of France. In their approach to science, Christian Huygens and Galileo Galilei shared a geometrical bent when it came to tackling mathematical and physical problems in the pure tradition of the ancient Greeks, and particularly Archimedes. This applies to fields such as optics, hydrostatics, and more generally the science of equilibrium of bodies, to problems of areas and volumes, and many others. The two men never met. When Galileo died in 1642, exiled in his villa in Arcetri, Huygens was just 13 years old, so didn't really have his education in the sciences at that point. From a certain point onwards, Mersenne, who had already sustained correspondence with Christian Huygens, began, at the latter's request, to write to his son. Indeed, a letter to Mersenne, dated 23rd December 1646, Huygens writes, "From now on, I will only serve as an address to the literary trade among you two." His son, whom he called my little mathematician, was 17 at the time. A few days later, dated 14th January 1647, Huygens writes to Mersenne, "You have too high an opinion of my Archimedes, but I know that he will never deny that you must have He will never deny the one you must have of him." This letter is a reply to one from Mersenne, dated 3rd January 1647, in which the latter comments on Christian's ideas on falling bodies, in which he tells his friend that he believes if his son continues to work the way he started, he will one day surpass Archimedes. The problem of falling bodies was of particular interest to Galileo Galilei, and we shall comment on this below. Christian Huygens was primarily a mathematician. He was a founding member of the Académie Royale des Sciences, probably the most notable Parisian mathematician. of his time, Gottfried Wilhelm Leibniz, during a stay he made in Paris from 1672 to 76, was his private pupil. The two men always maintained a rich epistolary relationship. In their correspondence, Leibniz often presented his mathematical works to Huygens, asking for his opinion. In the following sections, I shall discuss various scientific topics of interest to both the Galilei and Huygens families. For chronological reasons, I will consider questions concerning vibrating strings, falling bodies, the pendulum, curves, and astronomy in that order. These are all questions in which Huygens was interested from his youth. I will then turn to the problem of musical temperament, a question which was dear to the two Galilei and the two Huygens, and on which Christian Huygens did substantial work later in his lifetime. I will begin with the question of string vibration. For Galileo Galilei, this was a continuation of the work started by his father. For Christian Huygens, the work was also a tribute to his own father, whose favorite activity was music. I may have read all this. Yes, right. The upper octave, the tension of the string must be divided by a factor of 1/4 and not 1/2 in order to make the octave jump. So the string tension needs to be increased or decreased by a factor of 4 rather than a factor of 2, which is what the length would need to be multiplied or divided by. It is important to recall here, Mersenne performed a great number of experiments. Yep. Yeah, we already talked about that. This is okay. Yep. Galileo Galilei and Christian Huygens, Part 3, the falling bodies. We start by recalling a few facts which should help understanding the problem of falling bodies. During the Renaissance, measurements were made on objects dropped from the top of a tower, and it was noticed, a fact which was not obvious a priori, that heavy or very heavy objects dropped simultaneously reach the ground at almost the same time. It was also known that the speed of a falling body is not constant but undergoes acceleration, and it was thought that this acceleration takes place according to the sequence of natural numbers, a sentence which meant if we divide the duration of the fall of a body into equal parts of time, and if, during the first lapse of time, the body travels 1 unit of length, it travels 2 units in the second lapse of time, 3 in the third, and so on. In other words, it was thought that the velocity was proportional to time covered, or equivalently, and using again modern language, that the acceleration of free falling bodies is constant. Law of falling bodies are already contained in Aristotelian physics. Galileo got the idea of experimenting on falling bodies using inclined planes on which he dropped balls. This was actually a question on QI recently. No, that's a lie. It was on QI back in the old days. Force is proportional to the mass. So, yes, however, when you consider the force of gravity in both cases, most of the terms end up canceling out. And so if you look at, like, the force of air resistance, then yes, it is possible that there is an appreciable difference in the air resistance in both cases. However, when you compare the force of gravity on each one, how is that explained? When you consider the force of gravity on each one, then the masses of the objects themselves are effectively negligible. And this is also true if you just do it like hang on. Right, knew I got this out today for some reason. F is going to be G mm over r squared. Right, so if we want the force of a baseball and the force of a cannonball, right, G, M is the earth, and then M is the cannonball, little m, over r squared Alright. Alright, gravitational force. G is equal to 6.67 times 10 to the negative 11th meters per kilogram second squared. The mass of a baseball is approximately 0.1, we'll go with 0.15 grams. Or 1 times 1.5. 10 to the negative first grams. Mass of a cannonball anywhere from 1 kilo to 300 kilos, depending on the era and what it was used for. Yeah, you know what? Let's go with... let's make it easy here and make it 100... And actually, right, this is going to be negative 4th kilograms. Let's make it 1.5 times... Wait. That was not 0.15 grams. That was 0.15 kilograms. I already did that ahead of time. Man. That's a really small baseball. 1.5 times 10 to the... Nope, that's little g. Yep, you and I thinking on the same page there. It's too bad I didn't look earlier because you probably had said, hey, that doesn't look right. And again, kilograms was anywhere between like 1 and 1,000. So we'll go with like 1.5 times 10 to the second and say that this is a 150 kilogram cannonball. So the force of gravity, based on all this stuff, it's going to be this. Mass of the Earth is 5.972 times 10 to the 24th kilograms. All right, ads are about to start. That's just the, beginning of stream ones. So I'll see you all in 3 minutes. I'm just going to stay right here and keep working on this because literally we just started. So thanks so much for coming. Welcome on in, Raiders. Woo! No, okay, times 10 to the third. Anyway. Okay. So we've got all this. Now notice that I intentionally picked, right, all these values to end up being the exact same numbers. The only differences are the orders of magnitude of the masses. So that's it. The baseball, and realistically, right, if I were to keep everything together, we could even prove that using FB equals MB times AB, right? The force that we're talking about, and realistically, this is going to be, right, the gravitational force of the baseball is going to be the A of F equals MA in this particular case. So if we were to sub in all of this stuff, this is big G, M of the Earth times M of the baseball all over R squared, then we've got this equaling the mass of the baseball times, again, the acceleration of the baseball. So those go away. And it doesn't matter what you're talking about. The acceleration that the baseball is going to, or the acceleration of any object on Earth is going to be independent of its mass. Asterisk, right? Like we said before, the only real issue that exists here is that, and this Rex is going to be your 9.8 right there. The issue that exists now is that really this should be treated as differential equations, and yes, there is a linear term which is based on the speed of the object having a negative acceleration due to the air resistance. So it is a little more complicated than this. The Newtonian mechanics stuff works for objects in a vacuum, and it works perfectly, and we've already tested it, right? Like Apollo 15, I think it was. The astronauts brought a hammer and a feather out onto the lunar surface and then let them go at the same time within error. And they hit the ground within the same error. So, tea time. Nice. Got coffee myself. On the night before we drive to Manchester, fly to Norway. Woo! All right, so the number that we get there is going to be 6.67 times 5.972 times 1.5 divided by 6.371. The actual number that we're going to get out of this is going to be 9.3784. Some other stuff there. And again, with this being, right, like 3... I don't even know if we can have literally 3 oh no, it's only 2. So 9.4 times 10 to the, this is going to be, right, yeah, we got all of our units working out here too. So this is going to be negative 12. And then the 24 over there is going to make it 12 up top with the 6 on the bottom. So, give me a sec. Did I? Yes, I did. Okay. So, no, should be fine. Meters up top. Kilograms. Translated to meters. No, it's a force. Right, okay, sorry. This is newtons. Right. Oh, man. All right, 9.4 times 10 to the, and then here we've got a negative 11 makes this 13, minus 4 is going to be 9. So this is, again, expected what we were going to get in the first place. Then, with the m already factored in there, we need to divide out our mass again. So if we take 9.4 and we divide by our, I really should go back and redo this on the previous. So using the number we had as the exact value, and then dividing by the mass of the baseball. Well, I don't like that very much. Oh. Yeah, no. There was something much more important here that I definitely forgot. Oi. Super important. Jeez. 1.472 newtons. So realistically, like 1.5 is going to be our... I can't do 1.5 because that's awful. You'll see why in a sec. All right, times 10 to the... This is 12 at the bottom, which divides in the 24, which then also gets negative 12 here, so that's going to be 0. So 1.47 exactly as it is. Then the denominator of the other one is also 12, so we get 12. 14 minus 11 is 3. 1.47. There's more stuff after that, but again, we need to divide out the 1.5 that we had in the first place, and we get a right. A of the baseball is going to be equal to 9.81364, which again, we can only have it be to 9.8 because we only use 2 real significant figures throughout this whole process. And there's our meters per second squared. And then this one ends up getting you the exact same thing. It's just slightly different. G equals 10 in Kauser spheres. Yes. So high potential. Exactly good point. If we were to divide this, if we were to say, okay, well, this is 1.5 times 10 to the 0, and then we're just going to divide by our 1.5 times 10 to the negative 1 from earlier, right? Then we end up getting then we end up getting 10 meters per second squared. So this is the issue with rounding before you get to the actual end. So anytime that you need to discuss an answer, sure, get it to that point, then round it, and then feed that into your discussion. But do not use that rounded number for any further calculations, right? I know maybe your physics teacher will be like, yeah, you just do this. I disagree. Use the crazy big numbers with all of the other stuff and introduce your error all at once at the end. yes, in theory, if you've got your plus or minus bars, then yeah, sure. Use your plus or minus stuff throughout the calculation and then figure out where you are at the end by, confounding your errors and all that good stuff. You mean the constant we use for gravitational acceleration? It's 9.81. Now, the one that G, yeah, the big G. Yep, that was back here a little bit there. There. Right at the top. High potential, how you feeling? I've been poking in every so often, but haven't really heard much because usually you're sleeping because I'm in the UK. Mm-hmm. Yep. I get you. Nice. I was thinking maybe I have to go see if I can go to TwitchCon Europe. Probably not, but throw in a proposal for EduTwitch. But I think the timing's not going to work out on us, unfortunately. Yeah, Rotterdam. It's in May. Speaking of. I mean... Not doing anything else. It's going to be ridiculous, though. But, yeah. Hey, Zach, how's it going? Anyway. Anyway. Anybody interested in anything in particular? Let me know. But we are currently working through the. There we go. Discussion of Galileo Galilei and Christian Huygens and what their father's influence was on each of them. They both, the fathers, were interested in music and passed a lot of that information down to their sons. Their sons were then also interested in music, but like didn't pursue it as a career or much more than a semi-serious hobby. And they both worked out various items. So we were just on the section talking about the falling bodies. And again, we're saying that Galileo did a lot of work with using inclined planes to show that the acceleration on the inclined plane was identical for two objects regardless of their mass. And this is also another thing that Rex, I know, like, yes, acceleration due to gravity is then also mitigated due to mitigated due to the decelerative force, dampening force, I suppose, due to air friction, air resistance. However, I mentioned before, the basic idea was that he was using long inclined planes, which then did not allow these two objects to accelerate differently due to like anything else. So, he got like an iron cannonball and like something small, something else that was of a similar quality, but then like ceramic, something light, but then could be molded into something of approximately identical size. And in using both of these things, he was then able to show that it didn't matter what the actual substance was. It didn't matter what the density of the object was. It didn't matter what the weight or mass of the object was. That two identical objects, when rolled down these super long inclined planes, would then accelerate at exactly the same speed. Would accelerate at exactly the same rate. So, again, exactly asterisk, because here, sure, you've got to worry about air resistance potentially, but if you are dropping the things, then you have a lot of air resistance, but at the same time, it's really hard to see what's happening because they're moving pretty quickly. When he was able to roll them down long inclined planes, the air resistance is fairly negligible, and then the friction on the surface, he was able to make it, again, fairly negligible. And in doing those two things, he was then able to figure out that, this will make it as close as we can get it. And by letting these objects go on these long inclined planes, then they accelerated at the same rate. Or like, as close as we could make it out to be. So dropping stuff out of the Leaning Tower of Pisa, for example, is not on the menu. Right? There were too many other things that were going on. And it made it much harder to figure out if you were to try to do that, because again, now you've got these two objects where air resistance will matter on the lighter object. So something that is ceramic, if it's, a sphere of ceramic versus a sphere of iron, again, dropping it out of a building, you're now going to have a differential in terms of its differential behavior in terms of its air resistance. But long inclined planes still allow it to accelerate, still allow it to impart some friction force, but, oil it up or polish your inclined plane, and it won't matter. And as long as they're the same size, then the moment of inertia and same, theoretical uniform density, then we're going to be able to say that the moment of inertia, from our perspective in the modern era, moment of inertia is going to be, roughly speaking, identical, such that just rolling it is not going to cause a difference in their behaviors. The same cannot be said, however, of even if you did this with a hollow cylinder, right? A pipe. If you made a pipe out of iron and a pipe out of clay, and then you rolled the sphere of one against the pipe of the other, the sphere is going to win every single time, no matter which object you're using. It's crazy to do this, but it's true. So this is one of the reasons why cyclists now use like solid wheels rather than your standard hollow middle wheels. Right? By allowing the mass of the object to be spread throughout it, rather than concentrated around the rim, it ends up working out that it ends up having a lower moment of inertia, and then the cyclists have an advantage if they're using solid wheels instead of hollow wheels. It's crazy. And yeah, maybe there's some conditions that particularly work, but for the most part, if the mass of an object is concentrated around the outside, no matter what that mass is, and the concentration of a mass is uniform, then the uniform mass, even if the mass itself is higher, should impart a better turning rate or turning acceleration. Okay. Right, laws of falling bodies are already contained in Aristotelian physics. Galileo got the idea of experimenting on falling bodies using inclined planes on which he dropped balls, postulating that the law governing falling bodies is the same for an object falling on a vertical plane as on an inclined plane. It worked. The advantage of working on the inclined plane is that the object falls more slowly and thus lends itself to better measurement. In this context, it is important to recall that Galileo did not have a clock with which to measure time. Right? You've maybe got a hourglass, and those don't really work very well. Not particularly precise. In this context, to study falling bodies, he was led to devise ingenious devices such as the water clock That is, that he measured the elapsed amount of time by evaluating the weight of the water flowing from a thin pipe to the bottom of a large water jug. Such experiments are described in Discorsi e Dimostrazioni Matematiche intorno a due nuove scienze. Now turn to Christian Huygens, who was interested in the same question from an early age. In a letter dated 3rd September 1646, at 17, he wrote to his brother, also named Constantine II, I guess. AB is an altitude from which the weight C is dropped. I demonstrate in the first interval of time of its fall passes a spacing like here, CD. In the second interval of the time equals to the first, 3 such spacings, and comes as far as E. In the third interval of time, 5 spacings. In the fourth, 7, and so on. We'll continue to make greater progress each time, always adding to the last spacing twice the first one. In addition to this, I have demonstrated that if it is thrown in any direction, it describes a parabola. Of all this and an infinite number of other things that depend on it, I never knew the demonstration until I invented it myself. Huygens' solution was the same as Galileo's. Mersenne knew that this problem was difficult. In a letter dated 13 October 1646, he wrote to Christian Huygens about the problem, declaring in particular, "As I greatly honor your father, and as I believe it will please him in talking to you about your propositions of which you say you have the demonstration, I will only tell you about the last one, of which I do not believe you have the demonstration if I do not see it." He then developed his ideas about the falling bodies without reaching any definite conclusion. At the same time, he talks to his young correspondent about ballistics, parabolic trajectory of objects. This is a subject to which Galileo had made significant contributions. Indeed, Galileo was not only interested in the vertical fall of bodies, but also in the trajectory to which an initial non-vertical impetus is given. Hey, Sai, how you doing? Good evening and welcome. We are, in fact. I am looking through a paper on Galileo Galilei and Christian Huygens, and the influence that each of their fathers had on them, where their fathers were both interested in and had a strong ability in music and a love for music that they then tried to pass on to their sons. Their sons, Galileo and Christian, respectively, were fine in music, and then both committed their lives to science. In some ways, they also then went through and did some experimentation with musical stuff. So, kind of cool. You have a doubt in a theorem, can you ask? Absolutely. Go for it. If you're trying to make a perpetual motion machine, it's not going to work. Probably not, but have to say it out loud. All right. He discovered that this trajectory, unless the impetus is directed vertically, is always parabolic. And truthfully, when it's vertical, it still is parabolic. It's just that you can't see it. It's one-dimensional. A result that formed the basis of what was to become theoretical ballistics, a topic which was already of interest to Constantine Huygens, the father, before his son took up the subject in turn, being Christian. In the same letter, Mersenne writes to Christian Huygens that, for the trajectory to remain parabolic, the impetus imparted to the projectile must never cease, but qualities that are easily imparted, such as impetus, are just as easily and quickly lost. Violentum non durabile. To conclude on this subject, he says, "Nevertheless, if notwithstanding this consideration you believe that your demonstration is still valid, I will be pleased to if you communicate it to me. And then, if you have got it right, I will tell you to show this force, so that you can then determine the locus by which your effect must strike with more violence. I would add that the principles Galileo has taken from everything he has said about motion are hardly firm, and although in small heights the proportions follow fairly closely. In large, they are almost always lacking. 16 November 1646, Mersenne writes again to Christian Huygens, I assure you that I have so greatly admired the beauty of your demonstration of the falling bodies that I believe Galileo would have been delighted to have you as a guarantor of his opinion. In the letter to Christian Huygens dated 8 January 1647, which we already have quoted, in connection with the question of string tension, Mersenne once again addresses the problem of falling bodies in connection with his recent work, Novarum Observationum Physico-Mathematicorum, that he intends to send him soon after. Thank you so much for the follow. The angle between the line from the center of a circle joining the midpoint of a chord in the circle is twice the 1/3 of the measure of the opposite arc. Is that an Euler? No, is that a Euclid one? Yeah, it's pretty close. Ninth standard. Okay. Sloppiness off, stroke width. Good. One of the questions where you say it's correct or not. Yeah. Fair. Okay, so we have to find the center of the circle first, which, granted, you're probably given the center of a circle, but because I'm working, it's pretty close. Because I'm working without safeties here. All right, we'll call that center of the circle. Close enough. Angle between the line from the center of a circle joining the midpoint of a chord in the circle. Okay, so we'll draw one here, and we'll also draw one here. Right, so in theory, do I enjoy factorization? I enjoy teaching it more than doing it most of the time. Okay. Angle between the line from the center of the circle joining the midpoint of a chord line from the center of a circle joining the midpoint of a chord. Yep, thank you. Okay. It's the midpoint of the chord. On these, it's going to be slightly different, but nonetheless, they're going from one to the other like this. It doesn't actually matter, right, what actual direction it's headed, but nonetheless, these are going to be right angles. So every time we go to the midpoint, it is definitely going to be a right angle. If we want to, like, just do a basic little proof of that, and this is crappy drawing, but whatever, it's fine. assume there is a diameter from the center to where? To one of the ends? Oh, like this? Right, but where are the endpoints of that diameter? All right, so we can ignore that one if this is what we're doing. Hey Famish, how's it going? Angle between the line from the center of a circle, so a diameter that joins the midpoint of a chord in the circle. Yes, we're taking a quick break to talk with Sai about this particular thingy. Yeah, today we're talking about the Huygens Galileo connection. That both of their fathers really were into music, and then both of them were really into science. Like, seems to be an interesting coincidence. Okay, so we have a diameter. Come on. No, that's all right. And C, the chord. Now, if we just draw a diameter, which goes through the center of a chord, then you're going to end up getting a right angle every single time. Stream is breaking. Hey, Rushback, how's it going? Oh, probably me. That's fine. I'm not getting any drop frames, so... Oh, nope. Okay, I got 500 drop frames. But I have no idea when that actually happened. Ooh, yep, okay, it's happening. It's happening! So we are discussing a quick little theorem, in theory quick, that Sai brought in here. If you go by any other name, let me know. I do use OBS. There has been some updates that have been like not going through because Linux, and I also use Linux, Linux knows that there's an issue And so it's like, do not update. Do not update. You know what? So I think I know what they're going for. No, not necessarily. I think I know what they're trying to say, but that doesn't necessarily mean that it's actually going to. I think that maybe some wording needs to be fixed in it. Is this translated from a different language, or is that it? And is there a picture which goes with it? And just for everybody, these are our other awesome math friends +1. Slim from Academy of Useless Ideas, Dr. Gold from Actual Education, Don Factorial, Ian Stuckey, E to the 2i Pi, who is Zach, who has also been here, Meriwether Remark, Penn Center, who is also here, Phobostream, Physics and Depression, Talos Teaches, and the Tutor Wizard, and also Matt from Math Pond. Has Talos just been off on a break? Yeah, it's probably a bit stressful. Angle between. So if I were to take this, this is just kind of a random chord, but if I were to reorient this here, yeah, I feel like this is kind of hypothetical. Um, I think maybe they were saying that this right here, in radians, mind you, is going to be, let's call this S, and this here is going to be 2/3 S. That feels wrong. Especially since on a unit circle, they should be identical to each other. Right? If the radius is 1, then the angle and the subtended arc should be identical to each other. So, I think it is a an issue with interpretation more than it is an issue with, like, all of it. Angle between line from the center of a circle joining the midpoint of a chord in the circle is twice the third, so 2/3 of the measure of the opposite arc. That can't be right, at least not with my interpretation. Okay, let's then try a different one way out on the edge. Now we have to be able to play the same game with this stuff as we did with that one. So that's going to be the midpoint of the chord. If I did it right, which probably I didn't, it's fine. From here to here. Say that the angle is 2/3 of the arc. Oh, wait. Is it this? This one, oh dear. Oh dear. You really thought that was where we were going, didn't you? That's weird. There appears to be an issue with my tablet sometimes thinking that it's on a different window than it actually is. So that's fun. Okay. So no, that's always going to be half. Yes, I too like working with the general form of this one. managed to teach it pretty well to my students, but you know, it's one of those like they'll get it if they get it, but sometimes it's a little mean. Right, if we could set it up in such a way that the factors of A are Mn, the factors of C are Pq, then we will be able to get a factorized version mx plus p times nx plus q if B can be written as mq plus np. And if we can do that, right? If we can do that. If there exists a factor pair such that this is true, then we end up with the version below. So then we can show how that works with this by saying, okay, we're going to take mnx squared plus mqx plus npx plus pq equals 0. Hide that for later. We take mx out. We're left with nx plus q plus p with nx plus q. It better work, right? Otherwise we're in big trouble. And then here we've got nx plus q taken out from both, leaving behind mx plus p. Or we switch it up and make it mnx squared plus npx plus mqx plus pq, and flip it around, do it the other way. And then here we get nx times mx plus p plus q mx plus p, which then again take out mx plus p as the common factor, and then leave behind nx plus q. So C must be written as P times Q, and then if B can be written as, again, that was what, MQNP, we may factorize on the rational numbers. I guess. Eh, that's a terrible way of putting it. You're going to end up with rational zeros for doing that. Japanese multiplication? No. All right, ads are about to start. I need to sync my clock again. And I'll see you all in 3 minutes. Gonna go and cycle some water here. So thanks everybody for coming. And I hope you all are having a great week. See you very shortly. Thanks so much for coming. Famish, let me know how that works. Oh, Man, I got nowhere to put stuff. Sorry, needed to change the laundry, get a snack, pour something out, cycle the water, and then my spouse is also like, hey. What do you mean, Famish? The turning invisible or chair streams? Exactly. You came back just at the right time. Or wrong time, I guess. So famished, if you mean this stuff right here, then, you know, what's happening is that we have here, you have your 5 sticks and your 7 sticks, right? And then down here, you've got your 8 sticks and your 4 sticks. And what you're looking for is what are the number of intersections between each of these things. Well, this is going to be the product of each of these numbers individually. This is going to be, again, how many intersections are there? This is going to be 5 times 8. This one's going to be 7 times 8. This one's going to be 4 times 7. And this one's going to be 5 times 4. But it's not really 5 times 8 and 7 times 8 and 4 times 7 and 5 times 4. And this is also what other people are going to... There you go. This is also what other people are going to mention in the Common Core math classes, is that, well, this doesn't really represent just 5. It represents 50 plus 7. So really this is 50. And then here, this is going to be not 5 times 8, but 50 times 80. Right? 80 plus 4, 50 plus 7. It's going to be going that way. And then, similarly, we have 7 times 80. And then over here we have 50 times 4. And then 4 times 7 is the bottom. So we end up with these 4 multiplications going together. 50 times 80 plus 7 times 80 plus 4, right, 50 times 4. That's fine. 50 times 4 plus 7 times 4. All right, so this is 8 times 5 is 40, and then there are 2 extra zeros, so 4,000. This is going to be 56 plus a 0 is 560. This is going to be 20 with a 0 is 200, and this is 28. And then add it all together. This is how we get the ones on Pen Centers, like the pop quizzes on Pens streams so quickly, is that this is what we're doing in our heads instantaneously. Right? So this is also why when people say like, oh, well, you know, what use is Common Core mathematics when you're doing all this? The use is that you're looking at this and you're breaking things down to its fundamentals and then reconstructing them in such a way that your brain is automatically doing the math. It just reorders how it works based on how your brain works, because all of us individually do this ever so slightly differently, but we all get the same answer provided that we're doing the individual calculations correctly. When all of us become practiced at this sort of stuff, right? It's just second nature. So 4788, and then if you actually were to, go somewhere and check what is 57 times 84, right? There's 4788 for you. Needed Desmos. So this visual stuff is really just another route in, in order to get the math correct. So if we wanted to, we could also break this down like the second graders are taught ish. Right? Break it down all the way, and then here all we have to do is just combine them as individual values, individual numbers. They all get combined down into the end. So this is actually what a lesson in two-digit multiplication might look like for, third, fourth grade class. Is that you would break this down as, oh, hey, this cool thing that they do in Japan to teach people how it all works. Forget if they call it like matrix method or something else, but anyway. You get them to look at it as a series of multiplications, but then, what are you actually multiplying? And then how do these all get added together? Right? Turns out, if we break it down as 4 different multiplications, we make sure that every single number is appropriately represented. And then we add, recombine, do whatever else you need to, you're going to get the same answer as just somebody who could do the old way, which for us, right, 57 times 84, we take 4, we multiply, that's 28. We multiply 4 by 5, we get 20, plus the 2 on the bottom is 22. Right, and then we say, okay, now we're doing 80s, so we get a free 10 at the bottom, and then 8 times 7 is 56. We then multiply 8 times 5, we get 40, plus the 5 is 45. And then we add them all up. And lo and behold, right, we get the same number. But doing it this way is intuitively harder because what are you really doing, right? You have to think about how it is that you actually are trying to combine these things with multiplication. This over here is much easier to teach. I mean, the setup is harder, but it's much easier to get the students to do it themselves, where they don't need you to do an example out and then they do one themselves. You could be like, okay, so they've got this really cool thing. What does it look like they're doing? And you could ask all sorts of questions and try to get the students to figure it out for themselves with minimal input by the teacher. And argue in your groups about what does it mean? What does all this stuff do? How would a number of hashes end up figuring out how to multiply this stuff? Let them argue with each other, figure it out. And then there was also the Vedic system of multiplication, which is slightly different, right? This is how I learned it, except sorry, this one right here is how I learned it, except every time that we got a number that was bigger than 10 in the multiplication, that carryover would actually be up top, and then we'd do the multiplication and add the carryover. This is how my kids are being taught in Britain how to do it, where the carryover comes to the bottom. It's a footnote. And then you still do the multiplication, then addition, but now the improvement is that this doesn't get in the way when you move to the 8. When you're multiplying with the 8, all those numbers up top, you had to go across and cross them out. And if you forgot to cross one out, you might end up adding it to the other one. Here, there would be no issue with adding it, right? This 2 is not going to get added into this number down here in any way, shape, or form. It's not possible. Right? You might end up making this 2,228 instead of 228, but that's a different issue, and it can be managed. For instance, make sure that when you're doing this, you're writing the other number really small, and then that way you incorporate it into the answer and then ignore it. If you need to, incorporate it into the answer and then cross it out. Right? You could always do that. The Vedic system of multiplication, which was introduced in the Hindu Vedas, and yes, it is in the, I don't know if it's the Bhagavad Gita or one of the others, but it is in the Vedas themselves. It teaches people how to do basic arithmetic because it was that important to them that they incorporated it into their religion. This information is too important to lose. Okay, so their point is that we're going to get at least a 4-digit number. Right? Because, and they would know this automatically, because looking at this, we have the second digit times the second digit, which is going to get us something that is tens by tens is hundreds. And since this is bigger than 10, it's going to carry over into the thousands. Yup. I'm going to recommend Isaac Asimov's Foundation, by the way, if anybody's interested. Good book. The show, it's okay. I found it entertaining, but anyway. So, the point here is, how do we get ones? Right? How do we get ones? Well, in multiplication, the only way to get ones is if we multiply the ones by the ones. Right? So 7 times 4 is 28. So we do the 8 here, we put the carryover down here as 2. How do you get tens? Well, either we could do ones by tens or tens by ones. And so in doing this, we're going to multiply the tens from one of them by the ones in the other, which, by the way, is how we would set this up if we were doing it as a polynomial distribution. Right, the 50 would be multiplied by each of them, the 7 would be multiplied by each of them, or vice versa. And so here you notice that the 5 times 4 is 50 times 4, and the 8 times 7 is 80 times 7. So when you multiply those together, we get 20 and 560. So that's, wait. 56 times 8, yeah. 560. And then we're going to add them together. Right, so realistic, I think the problem is that when you're looking at this in the tens place, we're just doing the 5 times, or sorry, the 5 times the 4 and the 8 times the 7. We're going to add them up and add 2, which was the carryover. So rather than saying, 560 plus 20, we're going to go 56, 8 times 7, plus 5 times 4 is 20. So 56 and 20 makes 76, plus 2 is 78. 7 carry over, and 8 is going to be the number in the tens place. Okay. Then we go to the next one. We say, how do you get hundreds? Well, the only way to get hundreds is if we take tens by tens in this particular case. We don't have any hundreds, so hundreds by ones is all going to get a 0. So tens by tens is going to be 5 times 8 is 40, plus the 7 from below is going to be 47. And then here we don't have a way to get thousands, so that 4 just carries through. And there you go, same number. I was rambling on, so people might not have even noticed. So anyway, this is 3 completely different ways that you could conceivably go and do the multiplication 57 times 84. Right? Get the students to understand how the hash system works, the Japanese multiplication, and then say like, okay, well, how would we write that? That's where we get the stuff down here, right? Writing it all out. How did I learn it? Well, that's this system right here, which is just a bunch of taking this stuff and putting it into like a little grid format, essentially. How did the Hindus do it like thousands of years ago? It's this right here, which is the same essentially as what I learned, but more compact. And it allows you to do it when you're more practiced at it. Hey, Raven. Yeah, so we're discussing the different ways in which multiplication has been learned, taught, discussed, etc. So like I said, we were working with the Japanese system over here, which is a series of hashes. And by putting these sticks together, it effectively creates this array, which tells us what the solution to this problem is. And likewise, the Hindu Veda system here uses the combinations of how to get ones, how to get tens, and how to get hundreds, which then carry over into thousands. We do the polynomial form here. When we're trying to multiply all this stuff, we end up getting all of this again. And then the way that I was taught when I was in 3rd, 4th grade, this is probably 4th grade for me. We were doing mostly single digit by multiple digit multiplication in 3rd grade at the hardest multiplication level. I mean, generally, you don't want to do the hash method with, like, 2-digit by 2-digit is hard enough. A little bit of pickle juice. Good for the digestion. So yeah, you could actually do this with any size numbers that you want, right? This is just basically taking a spreadsheet and saying like, yeah, that'll work. This is basically taking a spreadsheet and being like, okay, 57, that wasn't the number, was it? Yeah, 57 times 84 whew, is the same as saying, okay, this is 50, this is 7, this is going to be 80, and this is going to be 4. Right? This is going to be a super boring method of doing it, but you can do it the same. Now, this is also how we do polynomial multiplication, right? This is 40 times 100, which ends up getting us, again, 4,000. This here is going to be 56 with an extra 0. This one's going to be 4 times 50, which is 200, and this is going to be 4 times 8, which is 28. Right? And then this is just going to be what's the sum of all these things? Right, and if we wanted to actually manage to write this out properly, this would be like, this is going to be this times that. This is going to be this times that. And it knew what I was doing. If you looked at it, oh, no, it's not going to do it now. Right, that times that. That times that. Right, so now we could even change the number and make it like 28 times 63. 28 times 63. I'm just go like that. Now we instantaneously get all this stuff. So again, this is what most of us are doing in our head. Just automatic. Don't even have to think about it. It just automatically happens. Anyway. Good times. So if anybody else has any other questions on this sort of stuff, let me know. For the meantime, we'll keep looking at the Galileo and Huygens history. Hey, look at that. We passed the halfway point. Okay. I assure myself that all this will be well worthy of your consideration, which I hope you will share with me, namely in what it impugns, meaning that his new work, Mersenne, shows this proportion is not correct. The proportion of acceleration by Galileo's numbers 1, 3, 5, 7, etc., which is also yours, and in that it contains many things which contradict certain principles of Monsieur Descartes. It's important to remember that Galileo did not have the tools of the differential calculus, which was developed a few decades later by mathematicians such as Leibniz, Newton, Huygens, Jacob, Jacob and Johann Bernoulli, and Marquis de l'Hôpital. In particular, he was not familiar with the notion of derivative to express velocity, and even less of that with the second derivative to express acceleration. To formulate his mathematical results, he used the geometrical language of the Greeks and that of Archimedes and of Apollonius. often expressing these results with graphical representations, speaking of deviation of the tangent at different points of the curve, or using similar expressions. In the passage at hand, Galileo is relying on the theory of proportions to set out in Euclid's Elements with its limitations. In particular, according to this theory, one is not allowed to divide by each other two quantities that are not of the same nature. For example, a distance and a time. I mean... It was therefore impossible for Galileo to define speed as a distance divided by a time, or to write that a distance is proportional to the square of time. He wrote, for example, that the acceleration of a body in free fall is following the sequence of odd numbers, 1, 3, 5, 7, meaning that if at time 1 the distance covered is 1, at time 2 it will be 1 plus 3, or 4. At time 3 it will be 4 plus 5 is 9. At time 4 it will be 9 plus 7, which is 16, and so on. In modern terms, it means that the distance covered is proportional to the square of time, i.e. parabolic. How tedious. So this is a discussion on a paper that was written in November, I think. December. Page 14. Yep, end of the year. So 29th December by Athanas Papadopoulos. Dr. Papadopoulos is... I found his credentials somewhere. I don't remember. Wrote a paper here looking at the interest that Galileo Galilei and Christian Huygens both had in music, which was inspired upon them from their fathers, Vincenzo and Constantine, respectively, who were both musicians of a... I don't know exactly. I think, like, high-level hobbyist, basically, because both of them had other jobs. And how their interest in music propagated down to their sons, respectively, Galileo and Christian, and how they, Galileo and Christian, were interested in science. So, was there some sort of connection between it? There are some interesting, like, similarities between the two of them, even though they never corresponded, they never met. Christian Huygens was born 13 years before Galileo died. So, like, they never met each other, they never talked. Christian wasn't interested in science until well into his teenage years. He became prominent, and his talent was really spotted when he was about like 15 to 17. So this would have been 5 years after Galileo's death, essentially. Within that time. Excuse me. Okay, beyond the law of falling bodies, Huygens wanted to understand why objects that are dropped start to fall. Even if the phenomenon is not surprising because we're used to it, the question remains legitimate. Why do things fall? Aristotle wrote extensively on this subject. As with everything he studied, he sought causes. The explanation he gave was that every object tends toward its natural place. Heavy objects toward the earth, fire towards the sky. Even today, despite the ancient and modern theories available on the subject, the question of why and how attraction works remains open, or at least very difficult to explain. I mean, the warping of space-time is not really a disputable subject. There is a mathematical framework upon which it works, and almost perfectly. So, like, all models are wrong, but some are useful, is something to remind ourselves here. Um, Einsteinian general and special relativity describe how it is that massive objects warp spacetime and thus cause the effect of gravity. Yeah, there's some argumentation in terms of like, we just found out, or we just discovered recently the Higgs boson, which appears to be why objects feel gravity, but it's still like that part of it is still kind of a hard question. Einstein's work on the subject is not really open for dispute, except to be more precise. Despite what the flat Earth community thinks. It is natural to see that Pierre Simon de Laplace, in his Exposition du système du monde, retains only Galileo's name for the problem of falling bodies. He writes, Exposition du système du monde, Paris, Imprimerie du Cercle social, rue du Théâtre Français, numéro 4, l'an 4 de la République Française. French Republic. If anybody has played Expedition 33, this is where the date 33 December comes from, is the French Republican calendar, which was in effect as of officially 1792. Galileo laid the first foundations of the science of motion with his beautiful discoveries in the fall of bodies. Geometers, following in the footsteps of this great man, have at last reduced the whole of mechanics to general formulae that leave nothing to be desired but the perfection of analysis. That is exactly what I said. Perfection of analysis just basically meaning we need more precise results. Galilei jeta les premiers fondements. Okay, it's just the French, literal French translation of what was in the book. But at the same time, he didn't do that elsewhere in this paper. That's a little weird. But at the same time, he attributes to Huygens the discovery of the relation between the problem of falling bodies and that of the motion of the pendulum. This transition from the oscillating motion, whose duration can be observed with great precision, to the rectilinear motion of the falling bodies is an ingenious remark for which we are still indebted to Huygens. And 55 is, again, literal translation, or literal wording. Thus, we shall pass now to the pendulum, whose motion is a part of the field of kinematics, which, at the heart of the work of Galileo Galilei and Christian Huygens, the study of the pendulum is closely related to the concept of a clock. Galileo spent the last years of his life thinking of the conception of such an instrument. In building a pendulum clock, Huygens realized one of Galileo's dreams. Let us see this in some detail. Galileo's name is also associated with the theory of pendulum. He is considered to be the first to advocate the study of isochronism of the pendulum, i.e., the regularity of its oscillations within a rigorous physico-mathematical framework, even though this regularity had certainly been observed long before him. He is said to have had the idea of isochronism in 1581 when he was 17, while a medical student, observing the sway of a candlestick. He was puzzled by its regularity and tried to confirm his intuition by counting the period of the oscillation, comparing it with his own pulse rate, which at the time, unless of course you're getting excited about the fact that you're discovering something new, your heart rate, roughly speaking, stays about the same. So it's the best they could do. According to legend, the swing was that of the chandelier in the Pisa Cathedral. Galilei et l'expérience de Pise à propos d'une légende, une étude d'histoire de la pensée scientifique, Gallimard Paris 1965. It's also worth keeping in mind here that, as noted above, in those days there were no watches or clocks to measure time. Much later Galileo wrote about this phenomenon in Dialogo intorno ai due massimi sistemi del mondo, Ptolemaico e Copernicano, published in 1632. This is Galileo's main writing in which he defended the theory of heliocentrism, theory which had been condemned in 1615 by the Roman Inquisition. This, of course, was the book that triggered Galileo's trial, which took place in the year following its publication. Mostly because, again, not because the science was heretical necessarily, but because he mouthed off about a few things. He was a bit fed up with the churches, like, well, you know, you need to give a reasonable Famish, do you really want that one? Because I invented something, and I will show it off. Oh, you know it, but Raven doesn't? Oh. That's not nice. Well, yeah, I put on the glove again. Yeah, we just finished a paragraph. That's fair. All right, so I had suggested to somebody once that if we were able to like stick a yardstick somewhere, and so my supervisor at the time had suggested that I start working on oh, okay. I'll still do it anyway. It's fine. So I had been suggested to do a series of inquiry-based learning problems in order to figure out like how to get students to engage more with the work, all that stuff. And one of the things that I did was I said, okay, let's come up with a bunch of, like, you're having a day out at a theme park. King's Dominion or Six Flags or Busch Gardens were all pretty close to us in Maryland. A couple hours, but still. So what we could do is like come up with a series of individual like events or rides or activities within the theme park that all corresponded to different things within the theme park. And so this was like, okay, well, what would happen if you were to take a yardstick somewhere and you mark a target and you throw a like piece of string to land. It's the stupidest thing in the world, but you know what? It works. You throw a piece of string and you're trying to aim for a specific target, and you're trying to figure out like, are you within the appropriate distance to win? Whatever it is, right? So you say the winning range. It's going to be like here. Your throw ends up in this particular location this time. So obviously you don't win. That's not symmetric. Okay. You know what? Don't even. Haha. I win. It's still not symmetric, but you know what? It's close enough. So if you're within the win range, then you win. If you are not within the win range, then you lose. And then all of your throws are going to be measured by like a computer, for example, if you're supposed to do this digitally, right? So on the back end, there's a programmer who's going to try and figure out where you are versus where the win range is supposed to be. So I started with, okay, how would you know the distance between any two numbers? Right? So take two numbers. How do you know the distance between them? Well, the distance is equal to, or very nearly equal to, the difference. So you want to know what the distance is between two numbers? Find the difference between them. Now, we automatically, usually, will just say, okay, well, take the bigger number and subtract the smaller number from it. Right? Because we just know, all right, I don't want a negative number. I want just a positive number. So in this particular picture, right, the number x is going to be the larger number on the standard number line. So x minus t is going to be the distance between these two objects. Okay, problem number one solved, right? We know that the distance is going to be approximately equal to the difference between these two numbers. Specifically, we do have to watch out, though, if our throw is on the other side of t, right? x1, x2, all that good stuff. Then that would say that, well, the larger number minus the smaller number would be t minus x. But how would you get a computer to know the difference between the two things? Right? You'd have to introduce a condition. So your if-then statement, essentially, is going to be, we're going to do x minus t if x is bigger than or equal to t. We'll just give the equal to that one. We could do it either way, because when they are equal to each other, we're just going to get 0. So it doesn't matter. Here, we're going to say if t is greater than x, or we could flip it around and say x is less than t. Right? So either of these work. It doesn't really matter which way you do it. In order to use this as a mathematical function, you don't want to have two outcomes that correspond to the same input. So our inputs over here, right? We just have to make sure that we're only using one of the above things every time we come out with this. So here we don't want to put the equality sign here, even though the number comes back the same, 0, for both of these cases. We don't want to have to burden the computer with any of this extra work. So don't bother with it. You just say, okay, we're just going to do when x is greater than or equal to t here, and then only when x is less than t here. If you want to flip it around and make it x is greater than t, strictly greater, and x is less than or equal to t down here, that's perfectly fine too. You can switch that to the other one. Okay, so this is a piecewise function. It's telling us that there are two distinct separate pieces. Well, the standard notation for this is that we're just taking our x minus t difference, and we're saying, look, I don't care what the sign of the subtraction actually is, because the only difference between them, right, this right here, t minus x, is the same as negative t, or go the other way, negative x plus t, which is the same as negative parentheses x minus t. So Literally, the only difference here is whether we have this negative sign here or not. So here what we say is, okay, this is the absolute value. We want the distance between these two objects as a positive number. How far apart are they? You could just tell me 2 miles. You don't have to tell me. When I say how far apart are they, I'm not asking for a direction. I'm not saying 2 miles north. In addition to the fact that, okay, which one would be north of the other, I don't know. Again. So this is the actual definition of absolute value. Is that it is a piecewise function with the conditions attached at the end. Now, I do like to use this one instead. Because what happens is we have the absolute value of x minus t is equal to the piecewise function x minus t when x is bigger, and the opposite value of that when x is smaller. Right, this also works really nicely because it's in a much cleaner format. Okay, so how do we work with that when we're trying to say, like, when we're trying to find out, like, whether or not the person ends up winning? Well, we want the distance to be measured from t to our x2 and to our x1 All right, we find the absolute value of these things. I, in fact, wrote it in the negative format, so that's fun. But it doesn't really matter. Realistically, I would want to keep this kind of standardized, so I say keep it as variable minus target as much as you can. It's not like it really matters, but it can maybe help you understand it a little better or something. I don't know. Okay, so what do we want? We want to know whether that distance that's given there is going to be within, less than, or potentially equal to, kind of depends on your mood, the distance between our target and the win value. Or rather, we have a win distance here. So is the distance that's being measured, absolute value, x minus t, going to be less than or equal to our win distance w? Okay. So we can start with the easier case, which is when we have x minus t is equal to w. What's this all going to look like when we actually get it working? Okay, so let's do x minus 2 is equal to 5. So this right here is saying that the distance between the two things we're subtracting, x and 2, is equal to 5. So there's a few ways to do this. One is that we just draw it. The distance between some x value, where we don't know where it is, and 2, the target value, the distance that we travel, is 5. Now, we could travel up the number line, we could travel down the number line. We don't actually have much of a opinion here in terms of which direction works better for us. And in fact, if we're looking at this, we need to check all possible values. So, starting from 2, if we go up, that's going to give us a 2 plus 5 is going to be 7. And since we say that the distance is 5, that gives us this value, exactly 7. And we are exactly 5 away from 2 in the negative direction. We can count, we can subtract if we want. This is going to be 2 minus 5, or 2 plus a negative 5, which gets us a negative 3. And again, we are at this location. So this tells us that x is going to be negative 3 or 7. Okay, now we can get a more complex situation-ish, where we have like x plus 7 equals 3. But this is really the same thing. It's just that it looks a little bit different. So how do we fix it? Well, this is not subtraction, but we can make it subtraction. The distance between x and the negative 7, the number negative 7, is 3. Right? Make it subtraction. And then what we can do is draw it from here. The distance between x and negative 7 is going to be exactly equal to 3. Where does that put us? Well, if we go up from negative 7, that's going to put us at negative 4. And if we go down from negative 7, that puts us at negative 10. And we are exactly that distance away, so mark those 2 points. Which means that x is going to be either negative 10 or negative 4. Et voila. And again, more complicated situation. Absolute value of 2x plus 11 equals 7. Nice. Right? How do we get this to work? Well, we do the same thing. This is going to be 2x minus negative 11 is going to be 7. Now, some people might say, well, I don't really like how there's like a 2x in there. That's okay. We'll fix it later. Yeah. I mean, my undergrads had issues with it, but they were also pre-calc students who had never learned it properly. So here, what I encourage is take the variable term and just put it down, right? 2x. There's a 2x somewhere on this number line. I don't know where it is. The target value that we have is negative 11. The distance away is going to be 7. Moving down from negative 11, we get negative 18. Moving up from negative 11, we get negative 4. That's going to put marks on those exact two values. Now, I would like to just end it here, but I can't. Because this is 2x is going... okay. Close enough, really. But 2x is going to be either negative 18 or negative 4. So that means that x is going to be, we can divide everything by 2. So negative 9 or negative 2. if you need to, you can always rewrite the stuff that's here. So we want to divide this by 2 in order to get just x by itself. So then everything on the entire board needs to be divided by 2 as well. All of our distances, all of our numbers, all of the values that we have, all of them are getting pushed down, scaled inward towards 0. Right? And this is also true if we do something else like 7 minus 3x equals 12. Okay, here, what I'm going to say is I want to turn this into just, this is the difference between 3x and 7. That's it, right? Subtraction means you have distance between these things. So just do that. Right, we're going 12 down, we're going, or 12 up, and we're going 12 down. Where does that put us? Again, 19, -5. Those particular exact values are where we're at. And then we have 3x, so we're going to take this and divide by 3 everywhere along the whole thing. Oh, look at that. The fractions are much easier to work with now because you don't create them until the last step. So x is going to be, in this case, -5/3 or 19/3. And then make sure you simplify your fractions. So in this case, I can't do it. But if this were 18/3, for example, then we'd need to simplify it to 6. Our distances up above, right? 12 over 3 is just 4, but we don't have to worry about that in this particular case. Which also means if this were, for instance, negative 2x plus 7 equals 6, right? I would want to rework this. This being a negative variable is going to mess up everything. Or we could just say, well, how about 7 minus 2x is 6? Because these numbers are commutative. Negative 2x and 7. You just switch the order. So 7 plus negative 2x, or 7 minus 2x, is now just the distance between 2x and 7, which is, again, 6. So mark up, mark down. We get a 13, we get a 1. Mark here, mark here. X is going to be 2x is going to be 1 or 13. And then x is going to be, again, cut these all in half. That's going to be 1/2, 13 halves. All right. So now what about inequalities? It's actually not too bad, because what we're doing is we're going to do the exact same thing that we had over there. We're going to say, okay, well, if we took x minus 2 and did less than or equal to 5, do we hit the end? No, okay. The distance between x and 2 is, well, at most right? The distance between x and 2 is at most 5, or is less than or equal to 5. So how do we express that here? Well, the distance between x, our variable, and 2, our target value, is at most 5. So still draw the same thing that we had earlier. With a distance of 5 away, we know that the boundaries are going to be at -3 and 7. But this time, we're including, right, at most. So that means that it could be right on 2. The distance could be 0. We could be at 2. Well, that'd be really cool. So we could put a mark here, or here, or here, or here, or here, 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 or here, or here, or here, or here, or here, etc., 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 all the way from -3, solid circle, to 7, solid circle. Oh, there you go. So x is going to be a member of the set starting from -3 inclusive and ending at 7 inclusive. There you go. Right? Like, it doesn't take really any extra work to do this. It's pretty cool. What if it was greater than 5? Right? The distance between x and 2 is more than 5. Well, I'm going to just copy all this because we're just going to reuse it. And then we're going to take this, and we're going to drag it down here. And this time, it's not going to include any of this stuff in here. Oop. All right, well, whatever. Close enough. Boop. There we go. It needs to be, the distance between x and 2 needs to be more than 5. So we have to be outside of this range. That could be all this stuff going that way, all the way out to -infinity. Or we could be from 7 all the way up to +infinity. As far as we want to go that way. What's happening at -3 and 7? What's happening at those locations? Can we be there? Well, no. It says we have to be more than 5 away. So we can't be at -3 or 7. Therefore, we input open circles. Every time, I swear. So because it's more than 5, we can't be at -3 or 7. It's got to be further away. So open circles, and that leaves us with intervals which start from -infinity and go to -3. Exclude -3. Union, because it's a separate interval, start at 7, go to infinity. Ugh, I gave infinity a hairpiece. All the rest of these are just basically combinations of what we did down here. So if we want something to be less than or equal to 3, then we're going to have these solid circles at -10 and -4, and then it's going to be less than, the distance is going to be less than, so it's closer to -7. So it's shading in. If it's going to be strictly less than 3, then it is going to be open circles at -10 and -4 and shaded in. Still. Right? If we have this 2x plus 11 is going to be greater than 7, then again, open circles at what ends up being -9 and -2, and if it's greater, then it's shaded out. If it's absolute value of 7 minus 3x is greater than or equal to 12. Then we have solid circles at negative 5/3 and 19/3, and we shade out. Because again, bigger distance. Need to be further away. Okay. Now how do you do it algebraically? Slightly different, slightly harder, but not really. What you should remember is what is the definition of absolute value, not what did my teacher tell me, because my goodness, what did your teacher tell you, right? I just pointed in my head. Not quite. Right? What my teacher taught me was probably I'm going to take the absolute value of x minus 2 is equal to 5. I'm going to say that this is x minus 2 is equal to plus or minus 5, and then do x equals 2 plus or minus 5, which means that x is going to be equal to negative 3 or 7, and then that's the end, right? Well, if we look at that compared to what we got back here for this answer, yeah, it's the same. Okay, but what about then? Absolute value x minus 2 is less than 5. Okay, most students say, okay, what my teacher taught me was x minus 2 is less than 5. And that's about where it stops. And then they go, there's something, and then x minus 2 is greater than 5. No, wait. Hang on. It should be, and it could be less than negative 5. Or it might be greater than 5, or greater than negative 5. You know, students do all sorts of things. 2 out of those 3 combinations are wrong, so you have to be careful. So what I do is I say, okay, stop listening to what your teacher told you and listen to what I'm telling you. All right, when it's an inequality, what you do, and in fact, no matter what it is, all right, even if it's just an equation and it's going to come out with the same numbers, it's a good habit to get into. Take your x minus 2 less than 5 and say, okay, what is it that actually gets replaced here? Because there was actually nothing in the definition up there that talked about your distance, your w. There was nothing in the definition that talked about w. It said what your absolute value was equal to. So the absolute value can either be x minus t or negative x minus t. Not the other side of the equation, not the other side of the inequality, this side. What is your absolute value allowed to be replaced by? So here, what I want you to do is to say that this can break into 2 scenarios. True. Either x minus 2 is less than 5, or, and this is where it does become a little bit tricky. So you have to remember how the inequalities work, right? I want, in this case, if we do a picture first, okay? If we do the picture first, we got the 2 here, we got the 5 here, we got the 5 here. This gets us a negative 3, this gets us a 7. What do we want to have happen? This is less than, so it's open. And they need to shade inward because the distance must be less than 5. We have to be closer to our target. So that's going to be all this stuff in here. Okay, now, somebody better be clipping this. What we do, no, I'll do a highlight later. It's all right. Okay, so what we do is we look at this and we say, in order to get this, what do we have to have? Well, deconstruct it. This is an inequality that looks like this, and that looks like this. And we only want the area that includes the stuff between them and not the outside. So the correct Boolean operator that we're going to use here is AND, because we want where these overlap each other. Right. I mean, this is a deconstruction, right? So x minus 2 is less than 5. And what's the other one? Well, again, we set up there that was going to be negative parentheses x minus 2 is less than 5. Same thing on the other side. Same other stuff, right? The only thing that we're replacing is the absolute value. The absolute value bars themselves are going to be the thing that gets replaced, because what we set up here was this absolute value is defined by this piecewise function. X minus t when x is bigger, t minus x, or negative parentheses x minus t when x is smaller. So that's what we have here. Okay, so now we have to look at this and say, well, how do we solve each of these individually? This one's easy. It's just add 2 to both sides, right? This is x is less than 7. Cool. And this side, be careful. Right? If you say, I'm going to multiply by negative 1, right, then you're going to get x minus 2 is greater than negative 5. You have to watch that, because when you multiply by a negative with these inequalities, that's what's going to happen. We are going to necessarily switch the sign. So one of the other ways to avoid that is to say, let's just distribute. Then we add x to both sides and subtract 5. This gets us a negative 3 on this side is less than x. I didn't have to move anything. I didn't have to switch signs. I didn't have to flip. How do we work with this? Well, either you could say negative 3 has to be less than all possible x values. That's that one. Or you flip it with the terms in exactly the same arrangement. X is greater than negative 3, which again, that one. Okay, so working with these things, you could choose which one you want to use. Trying to construct it that way in pretty much every problem. It takes some getting used to, of course. Well, you can flag this video and it'll get to YouTube eventually. I'm still working on December's backlog. Good news, right? I do have everything from December on the Simplex channel is up and scheduled for sometime this week while I'm gone. The Obi channel for gaming is still behind a bit, so I'm still working on beginning of. I mean, it is all current as of the 20th of January. So that is the last time I uploaded. It was almost a month ago. Ugh. And that's November. So I need to start uploading my stuff on YouTube and getting the Nine Souls stuff done. Against the Storm is up there. There's a couple more. What else? No, don't search. What are you doing? Elite. Nothing. Against the Storm has 2. That's it. I've got seven more videos that I can upload until I'm out. That's not true though. I still have all of the rest of them from January and February that are like ready to be downloaded. I just haven't downloaded them. Not subbed yet. Let me change that. Awesome. Thank you so much, Famished. As a reminder, subs on YouTube are free. You don't have to do anything in order to subscribe. And then you could just turn off the bell alerts so that it doesn't like keep pinging you with, oh, Obi released like 10 more videos. I do limit myself to 1 a day on each channel. So usually the upload time is 0700 UTC. So that's going to be 0200 the day before. Nope, sorry, 0200 Eastern and 2300 the previous day in Pacific. Woo! So, I think we're going to bail after maybe another couple paragraphs or something. Maybe before the next ad break, I think. We might be able to make it to the next ad break, or to the next, for another half hour or more. It's almost 1. But I need to upload more stuff on the Obi channel. I'll also grant you that currently the Obi channel only has 18 subscribers. Thank you, Famished. So there's a lot less incentive to do anything. But we'll be getting more regular uploads to both once I get back from Norway. Got a sub to everyone. Yeah, Slim, nice. I know Gold does. I'm probably subbed to his channel. Got to make it to 500, man. I know. The the Simplex channel is pushing 200, so we're getting pretty close. 40% the way there to monetization. I've got 735 followers here. Like, if you just anyway. So, what we've got here, right? I would suggest distribute the negative and then just make the x's positive by shifting around. Need 1,000? Oh. Okay, it used to be 500. Yeah, I don't post regularly enough for people to be inspired to like sub on YouTube. It's okay. I'm not too worried about it. And besides, when I go back to the States, it's not likely that I'm going to be a professional YouTuber, so. Alright, so let's do one of these harder ones. $1,000. Ouch. Okay. I mean, it used to be. I don't think it was even that long ago. Well, yeah, but like the ad revenue was, $1 every 1,000 views or something like that. I mean, it was really low. I'm sure it's lower now. Okay, so with one like this, right, we've got the absolute value of 7 minus 3x is, greater than 12. Again, we can kind of poke around with what we've got up there for the picture and see what it is that is going to change. Cup of coffee. Lol, where are you getting coffee from? It's 370 over here, and that's pounds. Realistically, it's about the same in the States. It's like $3-ish. 250 maybe. But I gotta tell you, a 3-pound Americano. Good stuff. All my friends love like flat whites and cappuccinos. I'm like, nah. Well, okay, but what kind of quality are you getting from that cup of coffee? 99-cent donuts. Yeah, good stuff. All right, so here, if we go with 7 minus 3x is greater than 12, okay? Greater than means we need to be further away, and oh, would you look at that, right? That's an or statement. We want to be here, but outside. And then again, to deconstruct this, it's got to be something that looks like that with something that looks like that. And when we want to merge these two things together, we got to consider both things. So we want this one. We also want this one. They don't overlap each other. So if you put and there, it's null. There's nothing, there's no overlap. So you can't combine them. So here we have to put an or statement to say I want the union of these two sets. I want these two things to come together, despite being mutually exclusive. Okay, or negative parentheses, 7 minus 3x is greater than 12. All right, and then here, we're going to do the same thing that we did before. We're going to add 3x to both sides to make it positive, and then subtract 12 to get the numbers on the side that's opposite the variable term. So here we've got a 3x. Here we've got a greater than sign, which is 3x is less than. And 7 minus 12 is going to make a negative 5. Divide by positive 3, and x has to be less than negative 5/3. Or, here we do negative 7 plus 3x is greater than 12. Add 7 to both sides to make the numbers on the side opposite the positive variable term. So 3x is greater than 19. Divide by 3, and x is greater than 19/3. Or x is less than negative 5/3. So that is going to tell us that this looks like, right, negative 5/3, 19/3, open, shade out. Righto. Anybody have questions? So, Galileo was working on isochronism in 1581 when he was 17 while a medical student observing the sway of a candlestick or candelabra, or no, chandelier. He was puzzled by the regularity and tried to confirm his intuition by counting the period of oscillation, basing it on his own pulse rate. In 1658, the same year, Huygens published the first version of Orologium Ossitalorum, and 16 years after Galileo's death, Prince Leopold de' Medici asked Vincenzo Viviani, a disciple of Galileo and later Torricelli, and who held the title of first engineer to the Grand Duke of Tuscany, to write a memoir in which he would formally clarify Galileo's contribution to the pendulum clock. 4 years before, Viviani had published a biography of Galileo in which he reports on the pendulum and its use in astronomy and medicine for measuring pulses, but Viviani did not mention there any work on the pendulum clock. In his report to the prince, Viviani claimed that Galileo had imagined such a pendulum but never built one. Galileo's son, Vincenzo Galilei, tried to construct one with the help of Florentine craftsman Domenico Balestri, but the project was halted after Balestri died. It happens. Viviani nevertheless mentions the name of a watchmaker working for the Grand Duke Ferdinand II, who built a pendulum clock a few years later, following an idea different from that of Vincenzo Galilei. At the same time, he acknowledges that Huygens was the first to build a pendulum clock. Volume 3 of Christian Huygens' Œuvre complète contains a document written by Viviani addressed in the form of a letter to Leopoldo de' Medicis, in which he reports on this question. So, 58, Œuvre complète, yeah. 59, Vincenzo Viviani, Racconto storico della vita del signor Galileo Galilei di Vincenzo Viviani, edizione nazionale delle opere di Galileo Galilei, Firenze, Barbara Editore, 19, Appendix 3. In this work, which predates Huygens' Horologium by 4 years, Viviani makes no mention of the idea of Galilei using pendulum to build clocks. Viviani only mentions the laws of the pendulum and how they have been used in medicine to measure pulse beats and in astronomy to measure the duration of celestial phenomena. Vincenzo Galilei, 30 years of age, was an illegitimate son of Galileo Galilei and Marina Gamba, with whom he had 2 other children, likewise illegitimate. Yikes. Wait. In which he reports on this question. Letter number 673b, 20th of August 1659, Appendix 1, same volume of Œuvre complète, mentions that Girolamo Tiraboschi, in his Storia della Letterata Italiana, 1785, quotes the Nouvelle Fiorentine of 1774, in which it is said that Senator Nelli owns a story of the pendulum clock written in 1659 by Vincenzo Viviani, according to which Galileo Galilei only imagined such a clock in 1640 but did not build it, that his son Vincenzo tried to build one with the help of Domenico Balestri, Florentine craftsman, but that, surprised by death, oh, he was unable to see it completed. I suppose many are. Ismail Bouliao, in a letter dated 9th January 1660, sent Christian Huygens a drawing that he had received from Florence depicting a pendulum clock begun by Galileo Galilei. And Huygens replied to Boulliau in the 22nd of January 1660. You have given me great pleasure by sending me the design of a clock that Galileo had begun. I see that the pendulum is as good as it is in mine, but not applied in the same way. For firstly, he has substituted a much more awkward invention instead of using the wheel, which is called de rencontre. Secondly, he did not suspend the pendulum from a net or small ribbon, but in such a way that all its weight rests on the axis on which it moves, which is undoubtedly the main reason why his method has not been successful enough. For I know from experience that the movement becomes much more difficult and the clock prone to stopping. Even though Galileo had the same thought as me about the use of the pendulum, this is rather to my advantage than otherwise, because I have done what he did not know how to do, and yet I had no clue from him or anyone else in the world that this invention was possible. The question of Galileo's possible discovery of the pendulum clock was regularly raised. In any case, it is certain that Galileo carried out a considerable number of experiments on the pendulum. Not only did he discover its isochronism for low amplitude oscillations, but also came up with the idea of using the pendulum swing as a means of measuring time. He needed urgently such a device for his astronomical observations, for which he used to appoint a person for counting the number of beats. To end this section, let me mention an excerpt from a letter addressed by Christian Huygens to Pierre Petit on 1st November 1658. As for determining the length of the pendulum of each clock, I would have done well to explain in general what proportion the vibrations for various pendulums have to do with their length. But all that concerns these proportions having been fully dealt with by Galileo, Father Mersenne, and many other authors, I did not feel it necessary to include it in this description. Everybody else did it. Why do you want me to do it? Pierre Petit was an engineer advisor, geographer, and then Intendant General of Fortifications to Louis XIV. He was associated with Pascal, Huygens, and other scientists. 64. Pendulum of the clock. Possible discovery from Galileo regularly raised. Questions. See the account in Écrit sur la musique. Ismail Boulliau was a mathematician, astronomer, translator of ancient Greek texts, librarian and world traveler, close friend of Pierre Gassendi, Christian Huygens, Marin Mersenne, and Blaise Pascal, and was one of the first foreign associates of the Royal Society. Sweet. In conclusion, it should be clear that before Huygens, Galileo had the intuition that the pendulum should be used to make clocks. Nevertheless, he was unable to realize this project, even though the desire to have an accurate clock haunted him for a long time. Oh no. Yeah. Okay. Oops. Curves. We'll leave it here and head on over to Dawn's on. Who else we got? Dawn is doing some Dark Souls Remastered. Nice. Coco Confession doing some Hollow Knight Silk Song. Pi plays Pokemon. Still working on Sapphire. Looks like they have still not advanced beyond where they have been for the last several months. Pi is not doing a good job. Expedition 33 over on Ouija's channel. This is somebody we rated on last Tuesday, for blueprints. So it looks like he is currently, yeah, doing Act 3, so all the way at the end. Possibly Returnal Act 2. And he's playing all over the place. Oh, because this is an extra live stream, so it's... Anyway. High Potential, doing some co-working and studying again. Just got up about half an hour ago. Casey Snow Art is moving and setting up the studio. Woo! She will not be... will not be probably doing art anytime soon, just because she's got to set up everything. But Denny Anduza over on Paleontologizing is, of course, discussing dinosaurs. And looks like currently doing... hanging out with Delta Rain, maybe? Talking natural history with video games. The lack of effect of vitamin C indicates that routine supplementation is not justified. Interesting. We could ask about that. Let's right over to Rexa Savage, who is doing she is a new-ish sort of streamer doing Elite Dangerous, is doing a, quote, voyage to nowhere. Provided we can. Yes, okay. So she's doing some exobiology. I will be off for the next week, so I will see you all later. Hope you have a lovely week. We're going to go say hi to Norway for you all, and hopefully see some northern lights. So maybe we'll post some pictures when we get back. I hope. Have a great week, and we'll see you later.